Hello everyone, this is Adhish. I'm a grade 10 student from Mumbai. So today's problem is equal beauty. The difficulty level of this problem is easy medium and you need to know the set data structure along with the lower bound function which is present in C++ and an important property of a medium of an array of n integers. I'll be using these two main techniques along with some casework to solve this problem. So in order for you to understand the median property, you should realize that the median minimizes the sum of the absolute deviations, So basically if we have an array of n integers and we want to minimize the sum, the s for every s belonging to the array of n integers, we want to minimize absolute value of s minus x, then it's optimal that x is the median. And a nice proof for this fact is given over here. So you might want to pause the video and understand this proof. And I'll be using this fact in one of the cases of the solution. So in this problem, we are basically given an array of n integers and we are given a function which is the beauty of an array. The beauty of the array is defined as the difference between the largest and smallest elements. And we need to partition array A into two arrays B1 and B2 such that B1 and B2 have the same beauty. And B1 and B2 don't contain the same index in array A. So they can contain common elements, but the same index should be present in either B1 or B2. So we need to make the array good by increasing or decreasing each value of the array. And we need to answer this for t independent test cases. So since n is up to 10 to the power of 5 and we have about 1 second, n log n is expected since the sum of n is up to 5 into 10 to the power of 5. So let's look at the sample examples to understand the problem better. So the two arrays which we are given are 4 to 6 and minus 2, 4, minus 2, 4. The first idea is that we should sort each of these two arrays because we just need to partition the array into two non-empty arrays. So we essentially need to take one subsequence from one array and the remaining elements which are not present in the subsequence taken will form the second array B2. So that's why it doesn't matter in which order we take the elements, and that's why it will always be convenient to sort the array when the order does not matter. So let's consider the sorted versions. Now let's consider what all possibilities are there for B1 and B2. So now I'll make an important terminology. Let's define B2 to be the array which has the smallest element in it. So let always B2 contain the smallest element. I mean B1 always contain the smallest element, because B1 and B2, it does not matter in which order we assign the elements to B1 and B2. So we could interchange B1 and B2 and still have the same values of the beauty. The only thing will be that B1 and B2, the notation of what is B1 and what is B2 will change, but it does not really matter whether B1 was 2, 4 and B2 was 6, 4, 4, or B1 was 6, 4, 4 and B2 was 2, 4. I mean, yeah. So the two partitions are interchangeable is what I'm trying to say. So that's why we can always define B1 to be the partition which gets the smallest element. So that's why B1 will always contain 2. Now the possibility for B2 is 4, 6. And another case is B1 contains 2, 4, and in that case B2 will just contain 6. So in the first case, the beauty of the array, I mean the number of operations required, will be 2 because we need to, and so for B1 the beauty is 0 and for B2 the beauty is 2. So we need to make the two numbers equal to each other, and that's why it takes 2 operations. So that's why the answer will be 2. And in the second case, in the second partition, the beauty is initially 2 and over here the beauty is 0, so we need to make these two numbers equal. That also takes two operations. So in either case we have two operations, and that's why 2 will be the answer. And for the next example, B1 will always contain the smallest element, so it will always contain -2. Then B2 can contain -2, 4, 4. In this case, it's actually not optimal. So like this will be one of the border cases which I'll be mentioning later, when B1 just contains one element. In that case, notice that we need to make B2 equal to, or all of the numbers in B2 should be equal. And that's why we basically need to choose a number in B2 which will basically be the number which all the elements in B2 will become. And now we can use the property that the median minimizes the sum of absolute deviations. So that's why it's always optimal to assign all numbers to be the median, because in this case the cost to get from here to here is 4 minus -2, which is 6, plus 4 minus 4, which is 0, plus 4 minus 4, which is 0, which is 6. And in this case, note that the cost is the sum of absolute deviations from the common number. So in general, if we let B1 be the smallest element and B2 be the new value of B2, if we let it be x, 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 all the way up till x, then this means that the cost or the number of moves which we need to get B2 to be equal to this will be the sum of the deviations. So it will be the sum of absolute value of x minus ai for all I going from 1 to n, and this is minimized when x is the median, as I just mentioned in the beginning. So that's why it's optimal to assign the value to be the median, which is 4. But this is not optimal because there's another partition. So this is optimal when you assign B1 to only contain one element. But if B1 contains more than one element, for example -2, 2, and if B2 contains the remaining elements, which is 4, 4, this means that the cost is 0, so the answer is 0, and that's why 0 will be the output. And another possibility would be if B1 is -2, 4 and B2 is also -2, 4. Even in this case the cost would be 0, because both the partitions have a beauty of 6 and their beauties are equal basically. So those are the examples. Now I'll be building the formal solution using one key observation. So the key observation required for this problem is that let's consider a general case where we know B1 and B2 and we know their beauties, and each of the two arrays have greater than or equal to 2 elements. So they are not border cases which contain one element. They have greater than or equal to 2 elements. So let's say that B1 is something like some random list of numbers, and we always keep them in sorted order. And let's say that B2 is something like this random array, and we know that the beauty of B1 is 12 minus -2, which is 14, and beauty of B2 is 8. Then the key idea is that in order to make the array good, in order to make B1 and B2 have the same beauty, we will choose a particular number. We will choose the largest or the smallest number and increase or decrease that number respectively. So basically the strategy in order to make B1 and B2 have the same beauty is that let's choose the largest number in B2 and increase it by 6. So we increase it by 6, and then both B1 and B2 have the same beauties, and that's why the number of operations is 6. So in general, we can always choose the partition which has a smaller beauty, and we can increase the largest number of that partition. So let's say that B2 has a smaller beauty, then we can increase the largest value of B2 by the difference by beauty of B1 minus beauty of B2, because we assume that B2 has a smaller beauty. If B1 has a smaller beauty, then we'll just increase the largest value of B1 by the beauty of B2 minus beauty of B1. And this takes beauty of B1 minus beauty of B2 operations. So that's why the cost or the number of moves required will just be the absolute difference between the beauties. So between the beauties of the two partitions. That's the first key observation. And I'll be building the rest of the solution on this observation. So if you had any doubts, write it in the comments right now and I'll answer them. So that's the first observation. Then now I'll be moving on to the key idea. So the key idea is that it directly arises from the examples itself. So we first fix the minimum of B1 to be A of 1 because the two partitions do not, the order of the two partitions does not matter. That's why we can call the partition which has A1 to be the A of 1 to be B1, and we can call the other partition B2. And in the general case for most of the partitions, except for 3 edge cases which I'll be mentioning, we have the following condition met, that B2 will contain A of n. So let's say that we define B of 1 to contain A of 1 in it, and it contains some other elements. And in most cases, B2 will contain an. Obviously, there will be one case when B1 also contains an, but that is an edge case which I'll be dealing with separately. So let's say B2 contains an. Then it's clear that the minimum of B1, the minimum element in partition B1 is A of 1, and the maximum element in partition B2 is A of n. Now further, let's assume that B1 contains greater than or equal to 2 elements and B2 contains greater than or equal to 2 elements. That's going to be because only over there we can use this key observation. Otherwise, there'll be edge cases which we'll need to handle separately using the property of the median, which I explained in the examples. So this is the general case. So let's call this general case, which is case number 4. Now I'll be dealing with the 3 edge cases where this general condition is not met. So let's dive into that, and then I'll be explaining what we can use to solve the general case. So the first edge case is when A of n is contained in partition B1 and not in partition B2. So let's say that maximum of B1 is an, because an is the largest number. So that's why the maximum of B1 will obviously be an. Even if an minus 1 is contained in B1, it's going to be smaller than an. So this means that the beauty of B1 will be an minus a1. And the reason for that is because the largest number and the smallest number in the whole array is contained in partition B1, and that's why obviously any smaller number or any larger number does not exist. So obviously the beauty will be the largest number minus the smallest number, which is an minus a1. Now we need to find a way to choose the elements in B2 to minimize the difference in beauties, because we realize that the absolute difference between the beauties of the two partitions will be the cost or the number of operations required, or basically the number of moves required. And that's why we want to choose elements in B2 to minimize this absolute difference in beauties. Now first of all, notice that there will also be some cases when so there are 2 elements in B1. Now there could be only 1 element in B2 or 0, or 2 elements in B2, or there could be 0 elements in B2. So if n is 2 or n is 3, we can handle that separately. So when n is 2, in that case the array just contains a1 and a2, and in this case the answer is going to be 0, because we can just put this in B1 and this in B2. So that's one separate case. Then when n is 3, the array contains 3 elements a1, a2 and a3. So notice that a1 is less than or equal to a2, which is less than or equal to a3. Then there could be only 2 possibilities. The first partition contains a1 and the second partition contains a2, a3. And the second possibility is that the first partition contains a1, a2, and the second partition contains A3. So in the first case, the answer will be the number of operations required to make A2 to be equal to A3, because the beauty should be 0 in both the partitions, and that will just be, the first cost will just be A3 minus A2, and the second cost for the second case is just A2 minus A1, and because we need to make both the numbers equal, and that's why the answer when n is 3 will be just the minimum of A3 minus A2 comma A2 minus A1 when n is 3. So now that we have taken care of these two small border cases within this case, which we'll take care of in the beginning of our code, now we know that n is greater than or equal to 4, and we know that B1 contains these two elements and B2 contains greater than or equal to 2 elements. So it's obviously going to be optimal to choose numbers A2 and AN minus 1 to be in B2. The reason being, the largest difference is obtained when we take AN minus A1. So the beauty of B1 will always be greater than the beauty of B2. Now we need to make beauty of B2 as large as possible, but it can't be larger, it can't be equal to or larger than, it can't be larger than B1, because AN minus A1 is basically a very large number minus a very small number. So that's why it's going to be very large. And AN minus 1 minus A2 is a smaller number minus a larger number. So that's why this difference is obviously going to be less than difference. And that's why it's going to be optimal to set B2 to include these two elements. So B2 contains these two elements, and we don't care about the rest of the other integers. So because we know that the second largest element is AN minus 1 and the second smallest element is A2. So that's why the beauty of B2 will just be AN minus 1 minus A2. And now the answer will just be the absolute difference between these two. So the answer for this case will be AN minus A1 minus AN minus 1 minus A2. So that's the first edge case. I'm going a bit fast with these edge cases because there are many of them. And if you had any doubts in each of these edge cases, do leave them in the comments down below. Now in the second edge case, let's say that B1 contains only one element, because one possible edge case is when B2, so when B2 is included in B1. The other edge case is when B1 contains one element, and the third edge case will be when B2 contains one element. So let's say that B1 contains only A1, and hence B1 is A of 1 and B2 is A2, A3 all the way up till AN. So this means that we need to make all of B2 to be equal to some number x, because the beauty of B2 should be 0. In this case, the beauty of B1 is 0, and we need to ensure that beauty of B2 is also 0, and hence we need to make all the elements equal to some common number x, and this means that the x will just be the median of these n minus 1 integers, and we can just find the median and use that to basically find the sum of all I going from 1 to 2, all I going from 2 to n, the absolute value of x, which is the median, minus ai, because we know that the median minimizes this sum, which I just mentioned again and again. That's why we can, that's why this is the cost in this case. That's the number of moves required in this case, because like each time, so let's say we need to make A2 equal to the median. That's why we need to increase A2 by these many number of operations, by median minus A2 operations, to make A2 equal to the median. And in general, for any I, we need to make AI equal to the median, we need to perform absolute value of median minus AI operations, and that's why the cost will just be the sum of that for all I. Then similarly in the edge case 3, when B2 contains only AN and B1 contains all the other elements, so B1 contains A1, A2 all the way up till AN minus 1. So in that case, we need to make all the numbers in B1 equal to some common number x, and we'll set x to be the median of the first n minus 1 elements. So we can compute that and set x to be equal to that. And the reason why that works is again because the median minimizes the sum of absolute deviations. So this means that the cost will just be, so notice that in this case when I refer to median, I mean the median of these numbers. So and when I refer to the median over here, I mean the median of a1 through an minus 1. So these two medians are actually different. The first median is for a2 through an, and the second median is from a1 through an minus 1. So don't get confused between the same word used. And now the cost is just the sum of all I going from all I going from 1 to n minus 1, and the absolute value of ai minus the median in this case, and hence this will be the number of operations required. So we have handled all the three edge cases successfully. In the first edge case, B1 contains only in the first edge case B1 contains both A1 and AN. In the second edge case B1 contains only A1, and in the third edge case B2 contains only AN. Now we can look at the general case, which is case number 4. So now in the general case, which is case number 4, B1 contains A1, B2 contains AN, and hence the minimum of B1 will be A1 and the maximum of B2 will be AN. Now we need to find out what the minimum of B2 is and what the maximum of B1 is. Because if we know what the minimum of B2 is and what the maximum of B1 is, then we know what is the beauty for B1 and we know what is the beauty for B2, and we can easily compute the absolute difference between the two beauties to get the number of moves required. Now we can perform two kinds of strategies. The first strategy is when we fix the maximum of B1, and the second way we can approach this is by fixing the minimum of B2. We can fix either of these two quantities by basically iterating the array from 2 to n minus 1 with this quantity, and we can compute the optimal value of the other quantity. So in my solution we'll be fixing min of B2. So let's say min of B2 is some ai, and we'll be iterating over all I going from 2 to n minus 1. Note that we already took care of the case when I is 1 or when I is n in the edge cases above, so make sure that you have understood them well, and that's why we can just iterate over all 2 to n minus 1 and claim that min of B2 is ai. Now we need to fix, or we need to find the optimal value of max of B1. Now an important idea over here is that we basically need to ensure that the max of B2 minus the min of B2 is as close to as possible as the quantity max of B1 minus the min of B1. We need to make sure that these two are as close to each other as possible. Now we know that the max of B2 is AN and the min of B2 is AI. So we need to ensure that this is approximately equal to the max of B1, let's say that is X, minus the min of B1, which is A1. So that's why we need to ensure that X is approximately equal to AN plus A1 minus AI. Now a good idea when we are trying to find the value of X, which is as close to a particular quantity as possible, is to find the first value of X, which is less than this quantity, and find the first value of X, which is greater than this quantity. So a good strategy in these kind of situations is find the smallest value of X, which is just larger than this quantity, and also find the largest value of X, which is just smaller than this quantity. And by finding these two particular values, we are ensuring that X is as close to AN plus A1 minus AI as possible, and hence the absolute difference between these two quantities is minimized. So to do this, we can use two sets. The first set will help us find the number which is just larger by doing a lower bound, and the second set will we'll need to use some clever strategy, because a set lower bound won't give us the number which is just smaller. So in order to solve that situation, the second set will contain the negatives of each number. So in the first set, we'll insert all. So this is a multi-set. Note that this is a multi-set because there could be multiple values which are the same. That's why we use multi-set. And so in the first set, we'll insert all the AI values, and then we'll do a set dot lower bound to get this particular value of x. So we'll do a lower bound on an plus a1 minus ai, and on the second set we will insert the negatives of ai, and we'll do a lower bound on the same quantity an plus a1 minus ai. So this will so the first thing will obviously give us the element which is greater than or equal to this particular value, and now it's important to understand why inserting the negative value will give us the element which is just less than or equal to. So I'll be proving that now. So the proof for why if we know that negative x is greater than or equal to the negative value of an plus a1 minus ai, if this is true, which is what we are doing in the second set, then we know that x is less than or equal to an plus a1 minus ai. By multiplying by minus 1 on both sides of the inequality, the sign reverses, so that's why this inequality holds, and hence we know that x is just smaller than an plus a1 minus ai, and hence we have successfully found the largest value of x, which is just smaller than an plus a1 minus ai. So using these two values, we will just take the minimum of the absolute differences in these two cases, and that's basically the number of operations. So this is the full solution, but there's a small issue, and the issue with that solution is we have not yet clearly defined what our partitions are. So let's look at that carefully and let's see what our partitions are. So we are saying that the min of b1 will be a of 1, and we are saying that the max of b1 will be x, and min of b2 will be ai, and the max of b2 will be an. Now there's a small issue with this, and that is we are ensured that the indices from I to n are taken care of in partition b2. So the indices from I to n have successfully gone into one of the partitions. However, the indices from 1 to I minus 1 are not guaranteed to be included in partition b1, and they can't be included in partition b2 because partition b2 contains elements which are greater than or equal to ai and less than or equal to an. That's why we need to ensure that x is also greater than or equal to ai minus 1, and that basically completes the whole solution. So after we compute the lower bounds for the two sets, we'll just ensure that we take the maximum of x, so x will be assigned to be the maximum of x comma ai minus 1, and then we can compute the cost. So the cost which will be computed is just the absolute value of the two differences. So the first beauty, so therefore, like just summarizing the final answer, so the final answer when we are iterating over all indices I, so the final number of operations will be the absolute value of an minus ai minus a1 minus x, where x is either the lower bound on where x is the maximum of ai minus 1 comma the lower bound from set 1 or the lower bound from set 2. So you will be so there will be two cases where we'll take the s. So it will be the either, so there will be two cases. The first case is when we take the lower bound from set 1 on an plus a1 minus ai, and the second case is when we take the lower bound from set 2, and we obviously need to take the negative value because each value is the negative of the element, so the negative of the an plus a1 minus ai. So using these two values of x, we can take the answer to be the minimum of answer, comma absolute value of an minus ai minus a1 minus x, because we know that an minus ai will give us the beauty of partition 2 and a1 minus x will give us the beauty of partition 1. And that's the full idea. Now I'll show you the code implementing the same idea. So before I show you the code, it's important to mention that when we take the maximum of b1 to be x, we need to ensure that x, the index corresponding to x is not equal to, or the position corresponding to x is not equal to 1 or I or n, and that's why we need to remove a1, ai and an from a multiset, and we also need to remove from both the multisets, and then we can compute x to be the lower bound on the first and the second multiset, and then we can basically take those two cases and compute the minimum cost for those two cases. So now I'll show you the code implementing the same idea. So in the code I use LL to represent long, then I use fast IO as always. For each test case I take in the value of n. I store vector long a of n plus 1, which represents the array of n integers, or n plus n integers, because I'm using one based indexing. I have two multisets. The first one gives us the lower bound, which is basically greater than or equal to, and the second one gives the element less than or equal to the particular value which we are searching for. And then I take in the input array A and I insert ai into multiset 1 and my negative of ai into multiset 2. Then I sort the array of n integers. If n is 2, we print 0, because the partition will just be b1 is a of 1 and b2 is a of 2. In the second case, when n is 3, the partition can either be b1 is a of 1 and b2 is a of 2 comma a of 3, or b1 is just a of 1 comma a of 2 and b2 is equal to a of 3. So these are the two possibilities, and in both the cases we compute the minimum quantity, the minimum number of operations, which I explained. Then we have three edge cases. The first edge case is when the min of b1 is a1 and the max of b1 is also an. Basically both a1 and an are contained in partition 1. This means that it's optimal to make min of b2 to be a of 2 and max of b2 to be an minus 1. So in that case the number of operations will be the absolute difference, and since this is greater than this, we can just take the normal difference because that will be positive. Then in the second edge case, which I explained, we take the median of the elements. So the second edge case basically means that b1 contains only one element. So that's why we need to make all the elements from a2 to an equal to their median. And you can just work it out by hand that the median of elements from a2 to an is actually n minus 1 by 2 plus 2 at spot. You can work that out by hand, or it's also the n plus 1 by 2 plus 1 at spot. That's the median for the elements from 2 to n. So we compute the cost to be the sum of absolute values of ai minus the median in that case, and we take the answer to be the minimum of answer comma cost. Then in edge case 3 we have only one element, which is an in partition 2. So in that case b1 contains a1 through an minus 1, and we need to make all these numbers equal to their median. So in that case you can verify that the median is just n plus 1 by 2. So hence we can just set the cost to be the sum of absolute values for this particular median, and we take the answer to be the minimum of answer comma the cost. Now in the normal case, which is case number 4, we need to basically iterate over all indices going from 2 to n minus 1, and for all these indices we know that min of b1 is a1, min of b2, or basically min of b2 is ai and max of b2 is an. Hence b2 partition contains elements from I to n, and b1 partition has to contain elements from 1 to I minus 1, or it can also go on to x. It can go on to position x, where x is greater than or equal to a of I minus 1. So we can find x using these two cases, which I'll be showing in the code now. So before that, we need to ensure that we erase an, a1 and ai from both the multisets. Erase these three numbers from both the multisets. To ensure no duplicate entries are there, the entries are there in the partitions, and basically we need to ensure that that x, the position of x is not 1 or I or n. That's why we erase these three numbers from the two multisets. And notice that since I'm using multiset, I can use s1.find to find that a particular iterator and to remove it. So that's why we need to use dot find. If you just remove s1.erase ai, that won't work because it will remove all occurrences. We want to remove only one occurrence which corresponds to the index I. That's why we just use the erasing the iterator corresponding to that particular occurrence of find, and in that way we just ensure that we are erasing only one occurrence. Then we need to find x such that the absolute value of an minus ai minus x minus a1 is minimized, and that's why x should be as close to this quantity as possible. That's why we use the trick of finding the closest lesser and closest greater. So for that we use these two quantities. Iterator 1 corresponds to the closest lesser and iterator 2 corresponds to the closest greater, and using these two quantities we can basically so the lesser quantity will be the negative of the element corresponding to the first iterator, and the greater quantity will be the element corresponding to the iterator of set 1. And we take lesser to be maximum of lesser comma ai minus 1 because x should be greater than or equal to ai minus 1, and hence we always need to take the maximum with ai minus 1, because only then partition 1 can only then we ensure that 1 through I minus 1 are contained in partition 1, and that's essential because we need to ensure that all elements go to either partition 1 or partition 2, and hence we do these two operations. Then we take the answer to be the minimum of answer, so we can just remove this variable. We take answer to be the minimum of answer comma absolute value of an minus ai minus x minus a1, and x is lesser and greater respectively, and in the end we just insert back. So reinsert these three numbers into the two multisets to ensure that we are to ensure that when we go to the next index we again retain the property that all elements are intact. So that's why we need to reinsert them, and in the end we just print the answer with the \n because we are using fast IO. And now I'll just submit this code to see that it gets accepted. So as you could see, my code got accepted, and the time complexity is n log n, and that's a bit tight because we have only 1 second. That's why it works just narrowly within the time limit. So I hope you like this problem and my solution for this problem. If you had any doubts in any of these cases, do leave them in the comments down below. And if you like this problem and my solution, don't forget to give it a thumbs up. Thank you.